Cloud. Please welcome Professor Aga.
Thank you very much for that introduction. Let's see, where is the talk? Somebody here, slides were supposed to be, here we go. All right, so we'll get started. Thank you for that introduction. So I'm going to talk about infrastructure. The last talk was a lot more entertaining than this will be, but hopefully this will be just as informative. I work in large-scale distributed systems, concurrent systems for the last 30 years. My book was published in MIT in 1985, and it's become quite a standard. And I'll talk about how things are evolving. So we're moving from the world of clouds to the world of IoT devices and smart cities and smart infrastructure. So the next stage in this whole development is going to be how to facilitate smart cities. So smart cities require, improving the infrastructure to facilitate smart sensor systems. For example, just in the U.S., the infrastructure alone is a $10 trillion investment. What we'd like to do is to monitor all this, to extend the life of the infrastructure, to provide real-time data, to provide information on how things are evolving. Maintenance of the infrastructure is a critical problem. And this requires cyber-physical systems. So what we're talking about here is then hundreds of billions of sensors into networks, feeding data into the cloud, but also massively distributed processing, because you cannot possibly, in fact, take all this data and process it centrally. So in particular, just to give you an illustration, we have worked on, I work for, started a startup. I'm a co-founder of a startup that we started last year to monitor civil infrastructure, the bridges in particular. It's the first project. So we did deployment for three and a half years, a demonstration project in Korea from this, based on this project in collaboration with civil engineers, putting in about 700 sensor channels with 113 nodes into the bridge. And this got covered by the New York Times and The Economist and so on. And the idea is the bridge can monitor itself. So currently what we do is to send inspectors every 2 years in the U.S. by law to go look at the bridge. And the bridges can often have hidden damage that the inspectors cannot see. The inspections can cost millions of dollars for a large bridge, and still we don't have data which is real-time data in terms of what's happening. In particular, for example, this bridge, there was a typhoon, and we could tell right after the typhoon, right during the typhoon, exactly what the response of every element of that bridge was. So every cable, every pylon, every element of this bridge, structurally interesting element of the bridge, has a sensor node. And this sensor node is doing high-frequency sensing to exactly what's going on. Now, this is just on a small scale. You're looking at huge amounts of data just on a single bridge being continuously monitored, and we can tell the load factors and so on. We've done projects on railroads. So here's a railroad. You can instrument this track and put smart sensors on the railroad. And as the rail car goes by, as you can see in this particular animation, you can then see the waves. The right side here isn't animating, but there should be a waveform showing exactly what the response is of the bridge. So let's see. This is always a challenge when you're not using your own laptop. But anyway, so you see the response as the train goes by. Actually, now the animation is not working. So I'll skip that, but there's a video of the animation. You can see it online on YouTube. There's a presentation from Embedor Technologies. So if you just Google my name, Embedor, you can see the illustration. So we can tell the load of every car that goes by, every boxcar that goes by, exactly what the load is, exactly what the response of the element is, exactly what the track is doing. And not only that, the bridge can call you back, the track can call you back and say, this section, it's going to go at some point. So that's just the example of bridges, but similarly we can monitor tunnels and dams and other kinds of infrastructure wirelessly, continuously in real time. All of this can be collected then, so you've got lots of massive distributed processing going on. Just like the human brain, if you think of the retina in fact gets orders of magnitude more information from the brain than it sends to the brain. So this is kind of intelligent processing that the retina does of the images that it sees. Similarly, you cannot overwhelm the cloud. There will be huge amounts of data, so you have to massively distribute the processing, make the smarts, and think of the entire structure now as an extended cloud rather than the cloud as a central repository. But at the same time, you want to sort of send the abstracted data, the important stuff, the information, back to the cloud for diagnostics, for auditing, for understanding what's happening with the structures. And this would be creating then a national grid of smart infrastructure, a repository providing data as well as control, emergency response in case of earthquakes or typhoons, and so on. So I'm going to spend the next 10 or so minutes telling you how we can program these things. My background is a computer scientist, and we are interested in building these large-scale structures. So these IoT applications then involve lots of distributed computing. They need efficient execution. They need distribution. They need concurrency. You have to have stability and robustness in these systems. And, of course, scalability is the key to getting it up from so going from individual nodes to millions, to hundreds of millions, to eventually billions of nodes. Now, concurrency is the area of my research for the last 30 years, starting from MIT and then at UIUC for the last 25 years. We know how to deal with large-scale concurrency. So today, all of the applications that you can think of, things like Twitter and Facebook chat, LinkedIn, all of these large-scale applications with millions of users, multi-user games, they're primarily being written in actor languages. Now, those are the family of languages that I defined way back. So, for example, Alex Payne, who is the primary developer of Twitter, explains why Twitter uses actors, uses Scala, because it has an actor library. And concurrency, it's a tough problem, but the actor library makes the job a lot easier. Similarly, Facebook engineering, talking about the actor model, saying how well it's worked for them. So, they couldn't have done it if they used languages like C++ or Java. The bottom line, and there are, of course, other languages like Python and so on that are popular for small-scale computing, but they don't work for large-scale computing. So I'll explain the characteristics of this actor model. It's very intuitive, very simple. What the model involves is breaking down the computation into autonomous concurrent pieces, which are called actors, and these actors do not share state. So much like we have lots of parallelism in this room, all individuals are autonomous, they're operating asynchronously, there's some coordination going on, you don't share a state. You have your own local state, you have your own computation that's going on in your brain. Each actor operates asynchronously, actors may interact with other actors, so it's a very scalable, decomposable model of computation, which breaks down the problem into separate units. So state is encapsulated in individual nodes. You have independent control. So much like object-oriented programming takes an encapsulated state and behavior, this is the next level of programming where concurrency is intrinsic to your way of thinking, to your way of programming things, with independent control, with messages coming in and out. So the actor has an interface, much like an object, but has its own control. It can receive messages. It can send messages. It can create new actors. So the amount of concurrency can increase, and your system can be scaled as needed. Now, what this gives you is the ability to do automatic load balancing, to provide fault tolerance mechanisms. The runtime can exploit resources on clusters, grid, on mobile nodes, on sensors, and you can have the communication and computation travel, not just the communication, but the computation itself in terms of these agents can move and migrate as needed. So we are able to do, for example, software updates on the fly by sending agents to do diagnostics, to upgrade the software, to examine the nodes, to provide security and turn the sensors themselves into smart sensors with their proposition and providing the concurrency that's needed. Now, what these actors do then is provide a bare bones language, much like you have sort of a basic language of sequential computing. This provides a language of concurrency, language of computation that is a language for scaling up concurrency. On top of that, then you need mechanisms to coordinate. So you can have these actors, but they now have to be coordinated in various ways. And high-level languages can simplify this coordination problem, both at the level of P2P computation. So, for example, in the bridge examples that I showed you, we get a hierarchical structure. We are creating data at a tremendous rate, hundreds of kilohertz. This has to be processed locally, and they talk to their neighbors. So you create a P2P network and a hierarchical network where there is smarts in the system. So the smarts are not all in the cloud, but they have to move into the systems for the systems to be able to scale. You cannot deal with sort of trillions of pieces of data in 1 second. Just to give you an example, at the University of Berkeley, they did a project to monitor bridge just for a single, put up the nodes for just a single day. The nodes were not as effective as our nodes. They had much smaller amounts of data. But to collect 10 minutes of data, because they used central processing, they said, we'll take the data, put it in the cloud. To collect 10 minutes of data, it took them 8 hours over the wireless sensor network. And then the nodes are dead, because you have to do energy management, you have to, communication takes a lot of energy compared to computation. Computation is a lot cheaper than communication. So in this sense, you have to have smarts in the system. You might keep the data for diagnostics. You might keep a data for a minute or two, take it offline. But if you want a real-time response in a system and you have billions of things going on, it's got to be distributed. It's got to have smarts in the system. Now you need synchronization. So this synchronization may involve P2P in the small scale, and I'll show you an example of that. And then I'll mention how we can sort of synchronize in the larger scale. So the basic fact of concurrency, what makes concurrent programming hard is a kind of inversion of controls. So let me give you an example. So very standard example, think of a producer. For example, you're pushing jobs to a printer. Think of a buffer like the print spooler that's keeping jobs. So you put jobs into the buffer, and then you have a consumer like a bunch of printers that get jobs from the buffer. Now, what happens? Well, you cannot do a get from an empty buffer. You cannot put things into a full buffer. In the world of sequential computing, what we would do is to ask the buffer, are you empty? Buffer says no, we'll say get, right? Give me a job then. And this works just fine. In the world of concurrency, you have many agents. So one agent says, are you empty? The buffer says no, but the other agent says, are you empty? It says no. It had one job. The first one gets it. The second one can't get it. So the state of the recipient is dynamic. It's changing. Its interface is changing. So if you think of the interface of these objects in your programming, it's dynamically evolving. It's not a static interface. So how do we deal with this? Well, we have to deal with this by providing methods for negotiating and putting contracts between these actors. Right? These actors have to say, okay, when I ask you, are you empty, you're no longer going to then become non-empty. Right? So if somebody asks, are you empty, then you'll have some reservation system and some timeout. So these are protocols, and these protocols then will get expressed as logical rules so you can do higher-level reasoning. When we move from this to a larger structure like the cloud, and from the cloud to an even larger structure like the national grid and smart structures and distributed, you cannot have microscopic control over the entities. They're autonomous, right? Like the national economy. What do we do for the national economy? Well, we have a central bank. What does the central bank do? The central bank manipulates interest rates, right? It's a macroscopic control lever. Similarly, you have macroscopic levers over the behaviors of large numbers of agents. You cannot microscopically determine exactly what each agent is going to do. So as we move to these structures, we're going to want the elasticity and the efficiency of the cloud. We want to be able to support mobility, and that's what the model does. By isolating the state, you can easily migrate objects, which is hard to do if you have shared state. If you're in the world of Java, for example, you have to move entire VMs. You're moving from VMs to containers. Why? It's more fine-grained, it's more adaptive. A large-scale project like the Orleans project, Microsoft now accounting for more than 10% of the Azure and growing body. If you have a very large application, you're going to do it in Orleans. Why? Because the Orleans is based on the actor model. So this provides a kind of migration which provides efficiency and elasticity and the scalability. So when you combine these sensor networks with smart sensors as you move into the smart city applications and IoT applications, you're going to have sensor networks, you're going to have mobile nodes, the person walking through, the robots, the drones. These are all mobile nodes. And then you'll have a cloud at the back end. And you want to use this kind of a system seamlessly, right? To remove the hardware limitations, to reduce the mobile energy consumption, and so on. And so you need support for mobile cloud computations, which provides code offloading under the right dynamic circumstances, depending on the dynamic variables, such as the bandwidth, the available energy on the mobile device, the available energy in the sensor, and so on. So we have built then for mobile cloud applications in this kind of scalable mobile distributed cloud, a research prototype at the University of Illinois, which bridges the gap between mobile applications and cloud computing. Because otherwise, you're in this mode where everything has to be central, and that simply won't scale. So you need the flexibility to be able to keep data, to be able to send things. And then what is critical here is separating the logic of the component distribution from the components themselves. So these actors have the logic of what is to be done, and where it's to be done depends on the dynamic conditions. And this dynamic distribution of the computation then is done at runtime based on the context, because you may have policies for security. Maybe you do not want certain data off the mobile node. You have policies for energy management. You do not want the mobile device to go too low. And then this will be traded off with the quality of the computation and with what is offloaded at what time and when to be able to customize things. And this is all enabled through the actor model. So this middleware that we provided allows for you to use parameters like the energy estimation, the network conditions, the performance of your devices, the target goal to create offload plans, to allow the stuff to be pushed into the cloud, to allow component distribution. So let me leave a couple of minutes for questions. Basically, it's a primer on technology that is essential for the future. New programming, of course, it's here for the last 5-10 years. It's grown in the space of the cloud, but now beyond the cloud, it becomes even more critical to integrate sensor networks, to do IoT applications and IoE applications as we move to the Internet of Everything. And this will allow us eventually to get the smart infrastructure which is necessary to have smart cities. And current methods of just having sensors that's sending everything to the cloud will not scale up. So, and actually, you can even see that at the level of the energy consumption of devices. We've gone from single core to multi-core because it's a lot more energy efficient. Power is related to the cube of the frequency. That means that your performance is related to the square of the energy. If you can take a lot more devices which are slower, you can spend a lot less energy, and that's the only way you can scale. So if you go to about 0.8 on your power consumption, you can have two devices that use the same energy, and you increase your performance to 1.6, basic motivation for multi-core. Similarly, the brain is a very efficient device in terms of energy. What it does is use billions of processing units. So massive concurrency is the future, both for energy management and for effectively creating these smart structures. Let me stop here.
That last bit makes me feel much better about my brain, so I'm happy about that. We have time for a couple of questions. So are there questions about that you'd like to address? and certainly there's somebody quite eager.
The concept of actors exists in things like UML and object-oriented analysis and so forth. And this concept of actors, is it the same? Is it related? Are they derived from one from the other? How?
Yeah, so I mean, in UML, the basic concept here of actors includes concurrency. So it's the concept you find in Scala, which is act language, in Erlang, in Orleans, and so on. And sometimes the word has just been used, has been abused. So in object-oriented programming, inherently there isn't concurrency. Or the concurrency is with a thread model, which is not integrated. Here it's an integrated model. It's existed since the 70s as an intuition in the academic world. And 1985, my thesis, which is still the primer on it, was the MIT Press book. Yeah.
Just a question about the security. Can it be compromised? Can the sensors be compromised?
Well, the more you distribute the knowledge, the more the opportunities for security to be compromised. On the other hand, when it's compromised, the amount of information you lose will be very small. So the trade-off really is how much resource do you want to spend on what. By building fault-tolerant structures, you can ignore the fact a single node might get compromised with some higher probability than if you were critically dependent on every node. So depending on the application, there's a trade-off. The price is, an economist once said, if you have never missed a flight, you're spending too much time in airports. So here it's the same as the banking system. They lose billions of dollars to fraud. It's a continuous battle. But if they didn't, they could gum up their system with so much security that you wouldn't be able to use your credit cards. So that's probably the mindset to take in this case. We don't want to build a Fort Knox. We want to build efficient security.
Professor, just want to know, so for the actor model, do you encourage mutability state or is it immutable?
Yes, it has to be mutable because if you have actors representing, for example, an airline reservation system, the seat is there or it's gone. If you have an actor representing, so it's got to have a state because the world has a state. Now, it can be done by extending a functional context like Erlang does, or it can be done by taking an object-oriented language and extending it in the right manner to make it actor-oriented. But state is essential. Only in the world of scientific computing can you get away without the state.
Hi. So for physical structures like bridges and stuff like that, right? If you were to use like Scala, the overhead of a JVM would not probably be ideal. So would you recommend Erlang in that case?
Actually, in this case, we developed our own custom language.
Okay.
So there are dozens of actor languages. I wouldn't build your own, roll your own. And that's what I teach in my programming languages class is how to build languages. I don't teach different languages. I just show them how to build languages. So we build our own structures and our own service-oriented architecture, very lightweight. Yeah, I wouldn't put JVM on sensor nodes.
I think what we'll do is stop at this point with questions. I'm sure the professor will be around and you can speak with him if you have other specific stuff you'd like to address. We're now going to take a break, and we're going to pick back up at 11:05, so I look forward to seeing you then.
Thank you.